Next, we're going to look at some applications where things will grow exponentially. And we've already seen one. When we did continuous compound interest, the interest accumulated exponentially. And we had an exponential equation that gave us how much interest accumulated after a certain amount of time given continuous compounding. That application satisfied an equation like this. I shouldn't use y, I'm using p in my notes, so I should use p here. So p of t equals p of 0 times e to the kt. P measures what's growing. P of t will mean p after a certain amount of time. So like in our interest examples, after 4 or 5 years. P of 0 would mean a base amount, how much there is at a certain time, or at a base time. E is our exponential function. K is a constant. And t is time. This right here is an exponential function. Let's talk a little about exponential functions first. We're going to need a little algebra in doing these, and as we do them, we'll talk about it a little. But let's just first make a couple observations about exponential functions. Exponential functions grow quite quickly. Here we have e to the x. So let's just say, so this right here will give us y equals e to the x. It goes through 0, 1, because e to the 0 is 1, and it goes up very quickly. If you take a function like the parabola x squared, that will not go up as quickly. So if you take y equals x squared, sure, it goes up, but it doesn't go up very quickly. One other thing you'll notice about the exponential function is for negative x values, e to the x keeps going down to 0. It never crosses 0. In calculus, that's important. In this class, we will also see that in our second and third types of examples, where instead of looking at a growth in this direction where things grow up very fast, we're going to look at a growth in that direction. And the last two types of examples, half-life and Newton's law of cooling, will cover that. What else? The exponential function, the inverse of the exponential function is this function. The logarithm function, the natural logarithm function. And remember how you get an inverse function. You flip it across the diagonal line y equals x, which means this point 1, 0, 0, 1 will go over to 1, 0. E, so these functions are what's known as inverse of each other. And that just means if you take one as the input for the other, they'll kind of cancel and you'll be left with x. I just stepped on the microphone. We'll see where this inverse property comes into play. Or maybe I'll just tell you now as a preview. How would you solve that equation? How would you solve that equation? Solve for x, I should say. How would you solve that equation? Well, the first one, get rid of the 2. You can do that dividing by 2, same as multiplying by a half. So you get x is 5/2. What about the second one? We want to solve it for x. Well, we have to get rid of the logarithm. How do you get rid of a logarithm? Well, we use this property over here. E to the log cancels out and you're left with x. So in other words, take e to both sides of this second equation. E to the left side is just x. E to the right side is e to the 5th. So here we use an exponential to solve that type of equation. How about this last example? How do we solve it for x? Well, we get rid of that e. How can we get rid of that e? Well, we use this second property, that the log of e to the x is just x. In other words, take a log of both sides. Maybe I should say like e to that second equation. And a log of this third equation, natural log. In math, if someone says log, it almost definitely means natural log. In a science class, that might be different. But in math, well, it's the second last week of lectures. And we're not going to talk about logs next week, as far as I know. But in math, if you hear log, it almost definitely means the log with the natural base e. But where were we? Solve this for x, take a log of both sides. The log of the left side is x. The log of the right side is log 5. And we'll have to solve some things with things like that. But this is what we mean by e and logarithm invert each other. You can use them to cancel each other out. Just like 2 and 1/2 cancel each other out with multiplication. 2 and 1/2 are what is known as multiplicative inverses. But let's look at an example. So we saw that interest can grow exponentially given continuous compounding. Populations can grow exponentially. So let's give some information. The population in 1950 was 2,560 million. So 25, yeah, okay, so 2.5 billion. 1,000 million is a billion. The population in 1960 was 3,040 million. And we're going to have 2 questions. Use these years, 1950, 1960, to estimate the population in, maybe I should write in over there. I might need all this space. Actually, I probably won't. In A, 1973, and in B, 2020. We'll use these years to estimate the population. Our first goal is going to be to find an equation like this. And to do that, we're going to use the years 1950 and 1960 to find our constant k. So I'll write first, use 1950 and 1960 information to find the constant k. And here's how we're going to do it. Well, we're going to treat 1950 as our base year, and then 1960 will be what happens 10 years later. So the population in 1950, we're not going to worry, everything's going to be in millions, so we can just leave it as the thousands, is what, 2560. So the population in 1950, 2560, e to the k to the t, well, t is going to be, in this case, 10, because 1960 is 10 years later. And in 10 years, this 2560 grows to 3040. And we're going to use this to solve for k. So let's do that. Solve this for k. Well, k is right there. So let's get rid of this number first. So divide everything by 2560. You could reduce that fraction. These are eventually going to be thrown into a calculator, so I don't know. I didn't reduce the fraction of mine, even though I normally would. Divide by that. Now you have e to the 10k. Well, we need to solve for k. We have e to the 10k. Well, we will use, well, I guess it's more this. We'll use that observation to solve. In this case, we're solving for 10k by taking a logarithm on both sides. Logarithm on the left. Logarithm on the left is that, log of 3040 over 2560. Log of the right is just 10k. Remember, log and e will cancel, and that's there. Solve this for k, so just divide by 10. So we'll say k equals 1/10 log of 3040 over 2560, divide by 10. And this as a decimal is approximately equal to, where I lost the number, 0.0179. So we need to estimate the population in these 2 years. All we did so far was find k. We actually didn't do any estimation. We just used our base year information to find this constant. And we're going to have to do that in all of the examples that we see. But once we find that constant, well, once we find the constant, we can find an equation, which is p of t. So I'll say, maybe I should say so. So p of t equals what? Well, p of 0, our base year is still 1950. So p of t is 2560 e to the kt. Once you find k, the only variable you should have is t. And e is a constant, so it's not a variable. Well, we have our equation that gives the population after a certain number of years. Now we just have to use these years to estimate the population in 1973. 1973, let t equal, well, it's year 1973. So you get 2560 e to the 0.0179 times 1973, which equals, I don't know. Oh, I shouldn't have written 73. I should have written 93. In my notes, I did 93. So I'm just going to change this to 93. So instead of 93, or instead of 73, 93. And you get some number. Now, many of you are wondering, why did I use 1993? Well, you are right in your wonderings. T does not equal 1993 here unless our base was year 0. Our year, or our base, is not year 0. Our base is 1950. So this T, remember, measures time from our base year, measures time from 1950. So in 1960, T was 10. Here, from 1950 to 93, well, that's 43 years. So you would not let T equal 1993. You would let T equal 43. Maybe I'll write, so that's 1993 minus 1950. T is 43 years after our base year, so that gives the population. So P of 43 is 2560 e to the 0.0179 times 43, which is approximately equal to 5,360. Well, this equation is approximately equal to 5,360, so the population is 5,360 million. Maybe I should write that. Yeah, I should write that. That approximately equal to is actually incorrect with that word million there. So I'll just leave it like that. That's not an important technicality. So after 43 years, the population grows to 5,360 million. And what about 2020? Well, for 2020, that's 7 and 0 years after 1950. So we need P of 70 equals 2560 e to the 0.0179 times 70. And that's approximately equal to 8224. That's actually equal to 8524. I said 82 because I was looking at 2. 8,524 million. So as you can see, well, I don't think the population is 8.5 billion. I think it's still below 8 now. But this model is actually not that bad for predicting. I mean, we use information from 70 and 60 years ago to get an approximate, and it's not that far off. But remember what we did here. We found this constant k. A good bulk of the work in these is interpreting the information you're given so that you can find k. Because once you find k, it's really just figuring out what to substitute and then substituting and solving. So let's look at another example. Next, we're going to look at exponential decay. Now, exponential growth occurred, well, let's get an e to the x function. Exponential growth occurred over here on the positive x-axis side, where as time went on, things grew quite quickly, and as they grow even faster, like interest. When interest is earned on interest, that can be measured with an exponential. Here, for exponential decay, we're going to look at the other side of the exponential function. And as x goes more negative, we're going to see that the quantity decreases, it decays. But we're also going to see at the beginning, it kind of decays much more quickly than it'll eventually decay. So let's look at this example. The half-life of radium-226 is 1,590 years. The sample has mass 100 milligrams. Find a formula for the mass after t years. Find the mass in 1,000 years. After how long in years will 30 milligrams remain? Well, it doesn't look like we're given too much information, but we actually are. Again, what we're going to want to find is a function like this, and to find that we need the k value. We're not given much initial information in numbers, but remember what the half-life is. So the half-life is the amount of time it takes a substance, or it takes half of a substance, or half of a given amount of substance to decay. So let's say, where am I? The half. That should say the half-life. The half-life is the amount of time it takes half of a given amount of a substance to decay. Half of a given amount of a substance to decay. And that's half-life. So the half-life, the amount of time it takes half of a given amount to decay. So if you have 1,000 tons of something, the half-life is the amount of time it would take before 500 tons remain. If you start with 100 milligrams of something, the half-life is the amount of time it takes until you're left with 50 milligrams. And in this case, we're given that the half-life is 1,590 years. So this tells us if we have 100 milligrams, in 1,590 years, we'll have 50 milligrams. So that actually tells you information about two different times. So we can use that to find k. So I'll say since the half-life is 1,590 years, we have, well, what do we have? The initial amount, 100, times e to the k times t. T is 1,590. So we have an initial amount, e to the kt equals what's left after 1,590 years. It goes from 100 to 50. So we start with 100, and in 1,590 years, half of it decays, so we're left with 50. Now we just want to solve this for k. So divide by 100. 50 divided by 100 is a half. Equals e to the 1590k. Solve this for the exponent, so we take a logarithm on both sides. So you get log of a half equals 1590k. Divide by 1590, so you get k equals 1 over 1590 log of a half. And in this case, we'll notice, where is k? I wrote it somewhere. I just had to go to my calculator. In my notes, I left it as this. And you can actually do these, leaving them like that. But I should use the decimals. So this decimal is, let's see, that's 10 to the negative 4. So we have negative 0.000435 9. Let's just use those numbers. Negative 4 point whatever. So we found our k value, and now we can answer part A. So A, P of t equals P of 0, which is 100, e to the negative 0.00043594 t. Now one observation I'd like you to make here. In this case, this exponent turns out to be negative. When you have an example of exponential decay, the exponent will turn out to be negative. The curtain, I don't know if you can see, I don't think you can see it on the camera, but I flung the marker out of my hand and a curtain caught it for me. It was awfully nice. But it made me lose my train of thought. What was I talking about? Oh, negatives. When you have decay, you'll get a negative k value because we're going to want the decay to occur on this side of the y-axis where the exponent would be negative. Another interpretation you could do is flip this around the y-axis so that you get a function that looks like this and go from there. We'll just leave it like this. So part A is that. Part B, find the mass in 1,000 years. Well, the mass in 1,000 years is P of 1,000. Here we're starting at time 0. We didn't say we're starting at like 1950. We're starting at time 0, and in 1,000 years you're at time 1,000. So P of 1,000 equals 100 e to the negative 0.00043594 times 1,000. And what do you get? I also didn't write this down. Oh no, I did. That's approximately equal to 65 milligrams. Did I answer the other? Yeah, I did, okay. So, and this answer, after 1,000 years, 65 milligrams, this actually makes sense. We can do a small amount of checking here. We know that in 1,590 years, we should be left with 50. So in 1,000 years, we should have more than 50, because not half of it has decayed. Only 35 milligrams have decayed in, 1,000 years. And what about C? After how long will 30 milligrams remain? Well, look at this equation up here. We have one independent variable and one dependent variable, so to speak. We have T and we have P, the amount of time and the amount of substance. In part B, we're asked find an amount of substance after a certain number of time. In part C, we're saying find a time that'll leave us with this much substance. So in part B, we're solving for P. In part C, we're solving for the time. And we want to know after how long will 30 remain. Well, then 30 equals 100 e to that number times t that number times t? Well, we just have to solve for t. So divide by 100. So I did 2 steps here. Divide by 100, that reduces to 3. I reduced this one. So divide by 100, that reduces to 3/10. Take a log to get rid of the e. So you get log of 3/10 equals just this exponent. Divide by that number, and you get t is approximately equal to 2,762 years. And again, that answer does make sense because, well, let's do a part D. Part D, why not? After how long will 25 milligrams remain? So same as part C, but 25. After how long will 25 milligrams remain? Well, there's the answer. Why is that the answer? Why is that the answer? Well, I did not substitute 25 here and go from there. That is not what I did. How did I do that? Well, we start with 100 years, or 100 milligrams. In 1,590 years, 50 are left. In another 1,590 years, 25 are left. So this one would just have to go through, what, 2 half-lives. I don't know if that's the proper physics language, go through 2 half-lives, but it makes sense in my mind. So after 1,590 years, 50 are left. After another 1,590 years, 25 are left. So we get that. You could substitute in 25 there if you want. Let's look at another example. Next, radon-222 has half-life 3.82 days. I think the previous example was also supposed to be radon. Not positive. I'd have to check the book. But here, radon-222 has half-life 3.82 days. Part A, how long does it take for a sample to decay to 1/1000th of its size? Part 2, how much of a 100 milligram sample will be left after 50 days? So first, before even answering part A, what we need is the constant K. And we'll use the half-life information to find that. Now, we aren't starting with a given amount, so we don't have to get fancy with our numbers. We can just use 1 and 2. If you start with 2, after 3.82 days, you'll be left with 1. So find K. 1 equals 2. You start with 2. E to the, what, 3.82 times K. So you start with 2. You're left with 1 after 3.82 days. So divide by 2. Take a log. Log of a half equals 3.82K. So K equals 1 over 3.82 log of a half. And you can find the decimal for that. I'm going to keep going with it written like that, and then at the end I'll tell you some decimals. So if you're doing these in like a calculus class, they usually just say to leave the answers like that. So let's do it like that, and then at the end I'll tell you the decimals. This is a negative because that number is between 0 and 1. So where were we? How long does it take for a sample to decay to 1/1000th of its size? Well, we have K, so we can get our P function, P of T, equals P of 0 times what? E to the 1 over 3.82 log of a half times T. Now we don't have an initial amount or an ending amount, but we can use initial and ending amounts given the question in part A. How long does it take for a sample to decay to 1/1000th of its size? Well, you can start with 1,000,000 and ask how long does it take for 1,000 to remain. Or you can use easier numbers and say, well, we'll start with 1,000. 1/1000th of 1,000 is 1. e to the 1 over 3.82 log of a half times t. Now our only variable is t. Start with 1,000. We want to know how many, in this case days, will happen before we're left with 1. So let's solve this for t. So you get 1 over 1,000 equals e to that number. So take logs of everything. So divide by 1,000, take a log of the right side. The log will cancel the e, and you're left with just the exponent. Divide by 1,000, you have 1/1000. Take a log of the left side, and you have log of 1/1000. Solve this for t. So we'll say t equals what? Divide by that thing, multiply by that thing. 3.82. I'll leave it like this. Log of 1,000 over log of 1/2. You could use properties of logarithms to simplify that a little, maybe. I'm not going to. So here we found our t. A started here. Here we found our t. What are the decimals? Well, k is a decimal. Is what? Negative. Where did I write it? Left it on my calculator. Negative 0.18145. 0.18145. And this time down here was like 38 days. I'll accept either answer, one written like that or one like this. That I should point out. Part B, how much of a 100 milligram sample will be left after 50 days? Well, here, we're still going to focus on this equation, this p of t equals p of 0, but here we're given a p of 0 as 100. We're given a time of 50 days, and now we just need to find how much remains. So p of 50, in this case, equals 100. E to the 1 over 3.82 log of a half. T log of a half is the same as negative log 2, but I like it like that. Solve this for t, or solve this for t. What am I doing? T equals 50. T equals 50. So simplify this left side. Well, that doesn't really simplify much. So I'll just tell you what this is approximately equal to. 0.011477 milligrams. And again, we can interpret this answer. This answer makes sense because why? Well, in part A, we determined after 38 days, 1/1000th will be left. 1/1000th of 100. What's 1/1000th of 100? It's that number. Which is that number. Which is that number. So after 38 days, we should be left with 1/10 of a milligram. So after another 12 days, we would expect the answer to be less than that, and it is. So exponential decay could look like this. It could also look like the next example we'll do, which uses Newton's law of cooling. So let's look at this example illustrating Newton's law of cooling. A bottle of water, 72 degrees Fahrenheit, is placed in a 44-degree Fahrenheit refrigerator. In 30 minutes, the water is 61 degrees Fahrenheit. Part A, what is the temperature in 30 more minutes? So 60 minutes after it was thrown in the fridge. Part B, how long does it take for the water to reach 50 degrees Fahrenheit? Well, again, our first goal is going to be to find K. But before that, we need one remark, or one rule, or let's call it a remark. Remark. Here, P of t, P of 0, measures temperature above, not above freezing, above the refrigerator temperature. need to keep this in mind for everything we're doing. I could, for this type of example, give you an equation that looks different and takes this into account. I think it's easier to always just keep this in mind than it is to have to interpret an equation that is slightly different, but it's really saying the same thing. So here we're just going to remember that P measures the temperature above the refrigerator temperature. So in this case, P measures the temperature above 44 degrees. First, we need to find K. We need to find K. So what do we have? We have, what, in 30 minutes the water is 61 degrees Fahrenheit. So let's find K in 30 minutes. So we have E to the K times 30. Okay, there's that. What is our base temperature? Well, our base temperature, the bottle of water starts at 72. And it gets to 61. But those are not measured above the fridge temperature. The fridge is 44 degrees. So what we would say here is the bottle of water is 28 degrees above fridge temperature. And at the beginning, after 30 minutes, it's 17 degrees above fridge temperature. So 17 was what? 61 without 44. And 28 was 72 without 44. So remember, we're always measuring this above fridge temperature. As a motorcycle drives by at 5 in the morning. So we have an equation that we can use to find K. Solve this for K. So we get log of 17/28 equals K times 30. So equals K times 30 divided by 30. And you get 1/30th log of 17/28 is K. This right here is a negative because the inside is less than 1, larger than 0. And what is this decimal? So K is approximately equal to negative 0.01663. Well, okay, we have our K values. Let's write our equation. So P of T equals the initial temperature, 72 without 44. The initial temperature above fridge temperature. So 28 degrees above fridge temperature. E to the negative 0.01663 times T. Now, you might be tempted to rewrite this, getting rid of the negative exponent, write it as a fraction. You can do that. You can do that. I didn't do it. A. I would actually say we leave it like this. A. What is the temperature in 30 more minutes? Well, let T equal 30. What happens when T equals 30? Well, I'll tell you right now, you get 17. What is the temperature in 30 more minutes? Well, in 30 minutes, the temperature is 61. What's the temperature 30 minutes after that? This is actually asking what is P of 60? P of 60 equals 28 e to the negative 0.01663 times 60. And what does that equal? That equals, well, let's look at our answer and let's interpret it. 10.3. So we're in a 44 degree fridge, and in an hour it goes to 10 degrees Fahrenheit. Well, that doesn't make sense. But remember, P measures the temperature above the fridge temperature. So this is saying in 1 hour, the bottle of water is 10.3 degrees above fridge temperature. So the water is 44 plus 10.3 is approximately equals 54.3 degrees Fahrenheit. And that answer makes sense given that we would expect it to be a little less than 61. Notice this actually illustrates the exponential growth better than the exponential decay. Here, the temperature of the bottle is decaying. But this one illustrates it a little better than the radioactive decay ones, because here we have in 30 minutes it lost 11 degrees. In the next 30 minutes it loses only 7-ish degrees. And in the next 30 minutes it'll lose even less. So in the first 30 minutes it loses 11. The next 30 minutes it loses 7. The next 30 it might lose 3 or something like that. It'll lose about 3 in the next 30. And so on. So as time goes on, it begins to decay less than it did initially. Part B, how long does it take for the water to reach 50? Well, we would want to solve this equation, would we not? We would want to solve that equation. How long does it take for the water to reach 50? Solving for T. And I have my eraser here, because that is not what we want to solve. That's wind, by the way. It's awfully windy tonight. Remember, P measures the temperature above fridge temperature. 50 is 6 above 44. So we would want to solve this equation for T. So solve it for T. You get 3/14, reducing that fraction, equals e to the negative 0.1663t. So it equals e to that, so take logs of everything. Divide, you get t is approximately equal to, where are we? 92.6 minutes. Which is how I knew in about 30 minutes I would lose another about 3 degrees. So here, we have a few different examples of exponential growth and decay. They all rely on this type of equation. And in all of the examples we did, the first thing we did, even before considering the parts we had to do, was find the constant k. Finding the constant k is very important. So try these examples. The process, you do get used to going through this process. I remember the first time I saw this was actually in a Calc 2 class talking about half-life. And I didn't really like it, but I eventually realized that an equation like this was all that really mattered. So try the examples and try getting used to dealing with equations like this. Find k, an initial value, a later value, and it factors in exponential growth.